Good morning, everyone. I am Suresh Vasu. I represent from the Intel India Private Limited, Bangalore, India. So my co-authors are Nithin, Venkatesh and Joydeep Maitra. So I'm going to present about my paper, Media Performance Validation in Emulation and Post-Silicon using Portable Stimulus Standard. So in the post-silicon challenges, there are lots of challenges what we are facing in today. So they are like a very high level of integration are happening in the SOC. So lots and lots of IPs are getting integrated, and it increases the lots of complexity of the SOC, and it's a very complex architecture which we are doing today. And there are lots of platform performance requirements are there, and also it's very competitive. So overall, the post-silicon challenges as we see today, so there are to do the validation, and from the validation engineer point of view, there are lots of challenges that are happening. We are facing it today. So from the pre-silicon point of view, there are lots of new verification methodologies are getting developed, or lots of things are getting used it today. But from the post-silicon side, there are lots of challenges today, but the validation methodologies, which is compared to the pre-silicon, I would say that it is much bit slower from the post-silicon part of, right? And from the post-silicon side, for the post-silicon work, the actual work start from the before the silicon itself. So we have the silicon preparedness phase. So we will be preparing for the silicon, and we would be developing our test content. We have to run it in emulation. So we have to ensure the test development happens properly. So once the silicon comes, and we have to use those content to validate the silicon. So as of today, we are doing lots of manual efforts today, particularly if you take in my media validation perspective. So there are lots of manual efforts what we are doing it today. So given the multitude of ways the SOC can be configured, like different IPs, interconnect topologies, number of masters, slaves, bus speeds, packet size, clock speeds, there are n number of combinations of SOC variants that comes into picture when I do the not only the functional validation, but when I wanted to do the performance validation. So performance validation is also key for my platform kind of SOS is what we are doing today. So we wanted a methodology which will help us to reduce the time what we are spending today to generate the test content. So because the most of the time what we are spending today is to develop the content itself. Also once the silicon comes, when I try to debug something, when the performance is not meeting, there are lots of tweaks are expected in my test content. So I enable that, disable this, because to debug that, there are lots of things I need to do that in the test content. So to do that, I should have that capability and flexibility to generate my test content itself. So that's a very big challenge as a post-silicon engineer what I face today. So here we propose about the portable stimulus standard, which really helped us to help us to resolve all these issues what we are facing with the post-silicon content generation today. So this is just a general standard flow of what we are using in the post-silicon for the emulation and also for the post-silicon. So usually we do the modeling of all the components. So then we do the scenario generation. There's a user-based composer will be there. The test contents gets generated. Once the test contents get generated, then we run it in emulator. Then in the emulation, so we create the logs, we debug using the logs, and also we develop all other performance counters using the which are available in the NOC or in the IP or from the DDR side. So all those logs we will use it and calculate the performance. Then also we have the coverage analysis, what kind of test content we have generated, what we are trying to validate, test intent, everything gets captured, and we reuse the similar thing, those test content what we have generated, similar thing we use it in the silicon as well. So that's a very general portable stimulus standard flow which I'm talking about. So before we go into how exactly the portable stimulus standard uh, used for us, just want to give just an overview of the what exactly we do in the media. So from the media perspective, typically we are doing the coding. So whatever the video comes, I need to encode it so that I reduce the bandwidth for the transfer. So with the minimum transfer rate, I'm able to transfer my video content. And once I transfer it, I regenerate the test content effectively, and without any quality loss, I'm able to uh, use it for by the use cases. That's my intent. So when I get an image or a video, I try to encode. There are lots of techniques that are available. So like spatial thing, what we talk about. So within one image or within one frame, what are the duplication of the data? What are the very high frequency data which is not visible to your human eye? So all those things I try to uh, remove it. So all the redundant data I try to remove it, so that I can easily transfer it with a lesser amount of data, and I can regenerate that later. And also the temporal thing, when I do the multiple frames between frame to frame, so there will be lots of redundant data. I do that motion estimation and all those things, and figure out where exactly the frame has changed. Rest everything I can remove it. So later on I can just I can transfer the data. I can reconstruct the data to do that. So then I transform that data. Then I can quantize. Depends upon the multiple quantization, I reduce the quality of my video. So then I reorder, then I do that entropy encoding. So that's another encoding which tries to reduce my bandwidth. I can transfer it much better. But typically in this scenario, there are lots of variants come into picture. The resolution, the formats, the bit depth, the quantization, how much I wanted to do, then whether I need to compress it, not compress it. That is more about the IP thing, and also my clock speeding and the DDR. We have like the frequency set points. What is the MTS we wanted to run? So there are a whole bunch of lots of features I need to enable, disable to validate my performance. So that's the requirement even to generate my test content or my test plan for the post silicon. So typical SOC, if you see that, it will be more with the codec and the multimedia. So it is what we will do. We will be having the multiple instances of encoder and decoder, and also we have the multimedia like graphics, display, imaging, and we traditionally have an OC and the memory, external memory DDR. So most of these masters will be doing all those transactions, everything. But my requirement will be, I need to create more stress scenarios, maybe the 4K, 8K, multiple frames, 30 FPS, 60 FPS. Then I should be able to create my concurrent scenarios. Multiple instances of codec will be there. Like I said, there will be multiple clock speed, knock configurations, multiple FSP frequency set points. Everything will be there. Then I should be able to create my end-to-end kind of scenarios where the codec will work with the other multimedia masters. Like codec will do the decoding. Maybe I need to display it, or graphics may render something, but I need to encode with that whatever the rendered by the graphics. So like that, there are lots of use cases. Everything comes into picture. So I should have a methodology to create all these things, chain it, concurrent it, pipeline it, all possible things. I should be able to do it. So why we chose the portable stimulus standard? So we came up with a methodology where the test content itself generated based on some images and some videos, and we have a C model, which the C model takes the input as an images and then videos, and I can pass different parameters to my C model. Based on that, it will generate me a test content. The constraints or everything which is passed to the C model itself is getting written in PSS takes care of it. So in the PSS, we write the constraints, what all features has to be enabled or disabled, everything PSS take care of the constraint, and then it passed to the C model. Then it helps us to generate me the test content. We can randomize my IP parameters. I will generate my IP test sequence, and also the same model, it will generate me the output reference data also. As per the test case, I maintain a whole database of images and videos, which I supposed to send to the same model. And all the parameters, whatever I want to constrain it, randomize it, that is taken care of the PSS. And finally, it will generate me the all test content, and also the output reference data. Once you do that, encode that, what will the expected data that generates me everything. So that's the whole methodology what we wanted to build across that. Also in the PSS, one of the major requirement for my requirement is, so the DMA addressing. So when I say I have an encoder and decoder, multiple instances are there, I need to always ensure that it doesn't overlap the DMA addressing. When at one place the image is loaded, and where it is going to generate my encoded image or decoded image, so all those things just should not overlap with the next master. When one JPEG, let's say one image I have, one JPEG, it does that, take the input from one location and does all the processing, dumps out to the another location. When the video encoding or decoding does, it has to be completely independent. That should not overlap. The whole addressing mechanism, it has to be taken care automatically. That is taken care in the PSS. And also when the multiple cores come into picture, because when I have the multiple instances of encoder and decoder, the multiple cores also come into picture. Each core addresses its own interrupt, and it is completely mutually exclusive. Everything is taken care. So that is addressed in the PSS. So how we have written that test content and the test cases, right? So what we do, let's say I have taken the component decoder and component and encoder. So in the component decoder, we have an action for the media backdoor loading images. And also for media, we have the action written for the media decoder. So after what we have written in the configuration, then all the input and output constraints have been written for the input encoded images, and all the constraints of the sizes, formats, quantization, everything is captured as a constraints. Then it to post it resolves all those things. For the encoder, for the decoder, what we do, we maintain a data set of the encoded image or the video, which is already encoded it. It is simply going to decode everything, and since the constraints have been written, all the constraints get resolved and it passed to the same model, and the input image or the input video gets passed to the same model, and finally it generates me the output reference data and also from the test content. The whole thing is taken care of by the PSS. And also for the encoder side, we have written the action media load backdoor and action media load encoder. So here also the input and output configuration, we have written the raw video here. So we maintain the data set of the raw video here, or raw images here. What it does, it picks that, and all again here the lots of constraints are written for the encoder C model, and everything gets calculated, addressing everything is randomized, and PSS takes care of all these things. So finally, it generates me the test cases and also generates me the images. What is the reference images? So input images, reference images, and all the constraints test content, it gets generated for me. So one general PSS code which we are showing here. So all the constraints are written. You can say that core wise, we have just made that multiple cores will be used into picture. And the size, we are seeing that random, it might be till 8K. We can use the different sizes. And also for the constraint media type, we have the video. The video means it can encode it, or image means it can JPEG, it can encode that. And also the constraint shape, we have written for the video, we can decode it, and for the image also we can decode it. And there are lots of other constraints have been written with this. So with these constraints, whatever written in that code, whenever when I wanted to generate the only the video encode it, I just give my raw data dot .wav file. Then I pass I select my video encode uh, media type. So below all other constraints have been written. What is the I have taken the raw video, and it has to be encoded, and how much I have to quantize it, and whether I want to compress it or not. So all those things get randomized, and the address buffering gets calculated, and also the number of frames I can select it, whether I want to run one frame or I want to run multiple frames, that also I can select it. So all those things gets constrained automatically, and it passes to the C model. The C model generates me the test content, output reference data, which it's supposed to be calculated. So the whole thing gets generated here. On top of that, for my performance validation, I also have the knob counters, and the IP performance counters are there, the media performance counters. The media performance counter, when my data start, when my frame starts and when my frame ends, there are counters which captures the each and every clock cycle, how much time it has taken to transfer my media data to the DDR for read and also the write. So how much time it has taken, how many bytes it has transferred, it has read, and how many bytes it has written. So all those things get captured in my knock performance data counters, and also the media performance counters. So all those counters values also we get used. So for all those counter values, there are small amount of APIs have been written that it is also used by the PSS, and when the test content gets generated, it includes all those APIs also. Once the test content is generated, the moment the DMA gets start reading the first frame, the counters get kick started. So when the first frame ends, when the interrupt comes, then automatically the counters are set to 0. So then we get the counter values to calculate our performance data. So that's how the whole scenario of my performance validation have been built across using the PSS. So also when I do the performance validation, right, it's not only the single uh, master. So I do the multiple masters for my performance validation. So let's say I have an JPEG decoder and also for the video decoder. So when I do the JPEG decoder, I use core 0. So let's assume that it tries to decode some 300 cross 300 image. And also I have the one video decoder where I need to do the 1080p. So that's an image which I can use it. So in this scenario, both the concurrent thing has to come up, and both are trying to decode that images, and both will be stressing the system. It might be using the NOC, it might be using the DDR. So it is trying to access the DDR. So we during this scenario also I calculate how much is the performance when these two guys do concurrently. What is it? First I calculate with the single master doing the decoding. Then I do that when multiple master comes into picture, what is the performance happens, how much usually I we calculate the performance a number of how many frames we were able to run, and so we are able to decode, we are able to encode. So it will be using the portable similar standard. The graphical representation of the test content is shown here. So when I do that backdoor loading of that particular image for image, and then I do the backdoor loading of the particular video here and the particular image here. So then it generates me that one particular core comes, and it takes care of that video part, and another decoder comes and it takes care of the image part. So that's how the whole thing has been done. And for the pipeline scenarios also we have, where we generate once the one master does, then the next master comes into picture. So it's to be pipelined. So that is also taken care of by the PSS. Once this gets finished, the next one should start. So that's has to be, it is completely pipelined. This is also taken care by the PSS. So it assigns the core, it takes care of all the DMA buffering, where for where the video decode happen, where the image decode has to be taken care. So everything is calculated by the PSS. So when we did all those things, the total uh, test content, how much time we have able to do that, right? That has reduced us completely 80% of my development time. Because when I do the multiple concurrent scenarios, pipeline scenarios, multiple core sample and to come into picture, then there are lots of SOC variants which I said I have to use this much clock frequency. The DDR I have to do this different frequency set points. Then I have a lot of IP features, enable that, disable that. The lots of study I wanted to do from the performance from the silicon data. The architects are looking for a lot of data from us. So then when I want to develop that much amount of the test content, I should have that methodology which helps me to so flexible and which helps me to generate me the test content instantly. So the portable stimulus standards really helped us to reduce my development content by 80%. And also all the concurrent and stress scenarios, it will be created very easily at the bare metal level. So the portable similar standards helped us to do that very easily, and we are able to also get the coverage very easily. How much coverage, what we have verified, everything just we got it from the PSS. And there are from our previous program to previous project to this project. So if we wanted to develop like 90 encoder scenarios, 90 decoder, 70 encoder scenarios, 50 decoder scenarios, obviously it has taken more than 3 months of our one engineer validation engineer's effort to develop the test content itself. So the validating that content is an extra task, but develop the content itself, it has took us 3 months of one man effort. So when we used that similar one with the portable stimulus standard, it has really cut down completely our development time of the test contents. So that has really helped us to reduce that. Also, instantly on the fly, when some ask comes, we were able to do using the portable stimulus standard pretty easily. So we never struggled. We didn't struggle to generate my test content. When I had to tweak something, when I had to enable, disable something, we're able to do it instantly. So conclusion wise, it made us reusable very seamlessly. Whenever I did the functional or the more effectively performance validation, what we checked in the during the emulation, and we were able to run the same scenarios at the post silicon, and we are able to correlate what was the expected performance, what we are really seeing in the performance. Also from the more scenarios which you wanted from the architect side or from the design side, when there was a request come, we were able to instantly generate our test content and measure the performance. So that's the beauty of the portable stimulus standard. So, and it reduced my manual effort. So in the amount of time just to write those test content, because of the concurrent scenario, because of the pipeline scenario, I need to calculate my addresses, where this has to be there, with where that has to be there, the whole DMA addressing, everything is taking more time for us to do the manual effort. So that has completely reduced, and it saves my test preparation time. So instantly I'm able to do, and I'm able to easily collect my coverage, and I'm able to generate my stress and concurrent scenarios, and I'm able to create my use cases and end-to-end kind of scenarios, like encode, decode, talking to display, or graphics talking to those kind of multimedia scenarios, interoperability of the scenarios, right? So that's how it has really helped us to do very effective performance validation. So that's the beauty of portable stimulus standard, I would say. So uh, uh, I would like to thank you very much for giving us an opportunity to talk about the portable stimulus standard work and how effectively it has used us for us. I would like to thank Tom and also Pooh for constantly giving us feedbacks to improve all our presentations. So thank you very much. So I'm open for questions. Thank you.